I wanted to give you a bit of a talk on how we are using CAPE-OPEN to enable some process simulations related to the green transition, and also looking a bit beyond in terms of getting modern equations of state into the process simulation world, where they are definitely put to the limits of their capability. So I'll start giving a short intro to Hafnium Labs and QProps, but then I'll go into these three examples. So one on the high fidelity dynamic simulation of carbon dioxide, then we'll go to where we're not utilizing carbon dioxide, but we're actually trying to remove it through carbon capture with Amine. And then we'll move beyond state-of-the-art thermodynamics, implementing polar PC soft and showing the validation of this, then as time permits. But what we try to do at Hafnium Labs is to solve one of the hardest challenges in chemical R&D, obtaining reliable physical property data fast. With fast meaning faster than experimentation or prediction of properties, and fast for process simulation means in the microsecond regime. And our QProps software is setting a gold standard for these property modeling systems, enabling better and safer design, faster developments, and broad exploration. We were founded in 2016, and since then we've been working on a universal solution, putting more resources into physical properties than any individual projects can justify, with more than 3 million euros already invested in our R&D. But let's see, what is the basic problem that we're trying to solve? Reliable digital designs, they require reliable physical properties. And if we take this example from Ralph Thorne, this is 20 years old, but it's ever true in the sense that you have two close boiling mixtures, ethyl benzene and styrene, and we run the simulation with two distillation columns in series and calculate the bottom styrene concentration in 3 different simulators, using the same thermodynamic models and same number of stages, etc. We get 3 different results, and either one of them is correct or none of them is correct, but how would you know? The differences are caused by differences in the parameters or in the even in implementation of the physical properties used. And the wrong physical properties can really ruin a digital design. This really causes pain points when we're looking at the green transition, because we have little or no data for green chemicals, and we're moving the processes into conditions that were not seen before. This really is a time-consuming process for the experts out there, having to revalidate against new data. And you also need to understand how reliable your simulation is. What is the uncertainty of your simulation? For new processes, we don't have the luxury of knowing this based on what we've seen in the past. And finally, solids, electrolytes, reactions are often neglected, but they can cause the most costly failures, for instance, due to corrosion. QProps overall is a platform technology, but a one-stop solution for all property needs. We separate it into 5 different products. Predict is using all data and all models to make the best possible predictions for properties of all compounds. That's produced as both products and services. The screen tool is doing the same thing in reverse, but trying to find molecules or mixtures that satisfy certain properties. But what we're talking about in this is the property package, which integrates a limited list of compounds and properties into process simulators. We also use a model tool on top of this, and I'll show you a bit on that, to tune and validate these thermodynamic models. And finally, I'll show you one example of using a unit operation as well, which can utilize a property package internally, circumventing a bit the need for going through the CAPE-OPEN. Now, we always build QProps with process simulation in mind. Both you can start from a process simulation knowing your compound's conditions. Then we run a workflow which is really about making sure you put your best foot forward. We get all of the data in one place. We create a project database containing the best possible property data, whether that's experimental data that has been measured or whether it's predicted data. We now have a set of properties that we believe we will be designing our models on top of. Then we can calculate properties and parameterize different thermodynamic models, benchmark them against each other, and finally export this into a single file that we can import through CAPE-OPEN in a process simulation. What's a bit special here is that since experimental data and property data was always part of the process, we're also exporting these. So you can always rely on a property package can be validated against the experimental data that was used to define that property package, and you can also retune it to match better the process conditions that you are looking at. But basically, we build QProps with extensions and integrations in mind, be it integrating in-house data, new custom models, or exporting them through CAPE-OPEN or to process simulators or to other tools like Excel. Then I'll talk a bit about how we are embedding QProps through CAPE-OPEN. There's a bit of an extra challenge because what we actually did was to build the entire core of QProps that's capable of performing flash operations, the implementation of thermodynamic models and so on. That's done in Julia, which is a viable alternative to Fortran and C++ due to its high speeds. But it's also easy to use like Python or MATLAB with a package manager that really handles all of your dependency issues. And there are more than 8,000 packages available on GitHub that you can also use together with your own in-house models. An issue that we faced when integrating Julia with CAPE-OPEN and also recently with the native extensions for HYSYS, Unisim, well, Hypertext simulators, was really that if you have, well, Jasper talked a bit about this earlier, but if you have a multi-threaded process simulator, this would like to get properties from different threads. But currently in the Julia 1.8, you're only allowed to call Julia from C through a single thread. So we have a synchronization point that really makes sure that you can only do this through one. In Julia 1.9, this will change, so we'll have to see how that can play along with the simulators, but essentially it could allow us to run fully multi-threaded. Now let me move a bit to some examples. And what we're really seeing is that the new processes that we're exploring this decade are pushing existing tools to the limits. And one example that we were doing together with Billington Process Technology was measuring getting some accurate properties for supercritical CO2 to simulate a Brayton cycle. The Brayton cycle for supercritical CO2 has potential for applications in, for instance, concentrating solar power, waste heat recovery, but it's also relevant in other parts. What's special is that it's basically a supercritical fluid. The temperatures go really high and pressures as well, but they allow advanced configurations leading to smaller turbo machinery than steam. Now, if you want to go and simulate such a plant in a process simulator, you're running into problems because the cubic equations of state or MBWR, for instance, they are not good enough at representing properties over such wide temperature and pressure ranges. And we are faced with using the Spahn-Wagner equation of state, also known as RefProp, but the speed of this is really too slow. And furthermore, you can see sometimes instabilities in the flash because of the difficulties of numerical solution with such empirical equations of state. They have multiple volume groups compared to the cubics, and that's really causing issues. So what I'm going to show you a bit is our effort. So we started out now I hope that you can see a notebook or a dashboard as well in the middle of this screen. What we're really showing here is how we approach validation. So we integrate all of the experimental data that's available for carbon dioxide, and we're now able to look at how well we can represent these data points. So now I've just added a few of them here, but essentially this is a process of a physical property specialist typically to validate that you are providing the correct properties for your system. Once we have those properties, we're now able to, let me just include those for the case where this was not working, but then we're actually able to now export it and include it in a flow sheet simulation. And what we start by doing is essentially to look at a simulation. Well, we set up the process simulation, and then we can look at what are the different conditions that are occurring in the flow sheet. And this can then be back validated together with the experimental data to see if we actually have data coverage of this simulation. The next step was really to make it a viable alternative to the built-in Span-Wagner. And what we really saw that when we started doing simulations, our QPROPS Ping-Robinson was about 45 times slower than the native Ping-Robinson, and the Span-Wagner was 250 times slower, meaning that it was completely infeasible to perform the dynamic simulation. So we started analyzing a bit on what was really the bottleneck, and you can really look at this as a delay function where there's part of it that's really due to the simulator. There's part of it that's due to the interface, that could be marshalling across the interface. In the case of CAPE-OPEN, it's really that this calc single phase property, for instance, is called many times. So it's a good idea to have some sort of caching after you've done a flash to quickly return the values that were done at those conditions. Then we had a special C++ Julia bottleneck part and a model. And we identified that actually the C++ Julia part could be improved by 1 to 2 orders of magnitude, and the model by a single order of magnitude. Then for the interface, we decided also, in addition to CAPE-OPEN, to implement the EXTN property package interface, which is used by HYSYS and Unisim Petrosim simulators, allowing us to compare this part of it as well. And we did some testing on a couple of streams in series, showing that we are now performing on par with the built-in Span-Wagner. Now, after improving the QPROP speed for the full simulation, we are now able to get to higher real-time factors than the built-in Span-Wagner, really due to the increased robustness. We do see that CAPE-OPEN is about 20 to 50% slower than the EXTN property package. But what is special about CAPE-OPEN is that it really allows us to use all of our internal flash algorithms, whereas the EXTN property package uses the simulated flash algorithms. So we actually expect CAPE-OPEN to give better results for mixtures. And mixtures is actually really key here, because even small impurities, like in this case 1% of impurity of oxygen and nitrogen, leads to great changes in the density just around the operating conditions of the compressor. So that's one of the upcoming works that we're looking at. Then I'm going to move on to simulating electrolyte systems. So we started building QPROPs really with electrolyte systems in mind, building high-performance reactive flash algorithms supporting multi-phase systems. Now we've been establishing a baseline based on published Amine models to see, well, okay, how do they really perform, setting up the workflows to do the same type of validation that we're doing that I just showed you for the pure component CO2 systems, but also now applying it to Amine systems. And then we're essentially moving on to integrating these in process simulations. There's quite a bit available already for Amine systems because they are of course used in the treatment of sour gas. So we have capabilities in the simulators already, and then there are plenty of solutions presented in literature that we have now implemented and validated against experimental data, providing an independent validation both for extended uniquark and electrolyte NRTL systems. We do these validations in sort of like a similar thing like we showed before in the Jupyter Notebook. Here we see the CO2 partial pressure versus the loading curves for the CO2 MDA piperazine system, and it's evident that there are cases where there's little correspondence between the experimental data and the model data. And so are we sure that our process ends up in the right conditions where our model is correct? That's where we are integrating and using the experimental data all along the way so we can actually validate that against the process conditions. For enthalpy of absorption, things are looking even worse. This is for an extended uniquark model. And also for the H2S, we see discrepancies at elevated temperatures. So let's make sure that we are applying the right model at the right conditions. That's essentially one of those messages. Now the system also contains ions, of course. So there's a complex speciation phenomena going on in these systems. For instance, here with piperazine at 60 degrees C with CO2, or MDA with CO2. And the simulators don't allow you normally to access this type of information, simply because they are built with apparent components, neutral components in mind. And the next demo I'm just going to show, let's see, this should actually get a video in the center of the image. This is just showing how we are adding a thermodynamic package for this sour gas that's extended uniquark for the liquid phase and SRK for the gas phase for an MDA system, where we are then subsequently, we're adding a stream, and then we're going to add a unit operation that is also using Julia. So this was based on the Q models. But we'll be adding a unit operation that allows us to look into the composition of that stream. Now, the custom properties that Ross Taylor was just talking about could be an alternative, but they're not supported by every simulator. So for us to be able to expose this type of information in all of the CAPE-OPEN capable simulators, we have to provide a different means, and this unit operation is how we've come up with so far. So we essentially add this QStream inspector Julia file, which is a script file, and you can always replace the script. We can turn it into a reactor. We can turn it into what we want. But in this case, we actually have a special situation where we are using the same property package in Julia that we are using in the simulator, but we are actually circumventing the overhead of calling into the PME, which will then get the properties from the PNC. Once we've solved this, we are able to view the unit operation. We get another user interface for that, and that allows us to access all of this additional information, such as the true composition, which I'll just save here. So we see this protonated MDA, there's different concentrations of carbonate bicarbonate ions and so on in the system. we can also, through the unit operation, expose certain properties like the pH in this case. The final case that I wanted to show you is really about implementing new thermodynamic models. We wanted to make it easy in QProps to implement and integrate and test these new novel thermodynamic models. What is nice about working with Julia and Jupyter, for instance, is that you can really document in a nice way what you're doing when you're implementing thermodynamic models. Now, we won't go into each of the details here, but Polar PC-Saft extends the original PC-Saft. It's built by Ben Marshall and Kostas Bokis from Exxon. And it's a relatively simple term that needs to be added onto the Saft equations in order to account for polarizability of molecules. And we can implement this in this notebook. And because of the integration of advanced global phase diagram algorithms and so on, we're now able to really validate this against the experimental data. So that's what we see here essentially. These are the global lines, and cyclohexane benzene are really close boiling mixtures. That's very clear from this as well. But we are able to now take this and validate against all of the experimental data that's available. These are pure predictions from the model with 0 binary interaction parameters, and it's able to capture accurately the azeotrope of these systems. So having this type of way to quickly validate new models that appear in literature is key to be able to support novel chemistry and novel molecules that are coming out of the green transition. And well, these models, we won't have time for that today, but they export essentially to these type of JSON files that contain all information about the model, including definition of the models in each phase, parameters, experimental data, reactions, fit strategy, and so on, in a way where we can really trace back what is happening when you're showing this in the simulation. That's what I wanted to tell you today. So thank you for your attention, and if you have any questions, happy to